Okay, good day everybody. I just thought I'd take some time to just produce a very short video, just maybe trying to interrelate some of these physics concepts that you've looked at with Dr. Youssef with physiological aspects. You may not know from this diagram, but I will label a few things and it might make a bit more sense. In blue, what we have here is we have a cornea. In green, up here, we have a lens, and in red, we have the retina. So this here, obviously, this up the top, is a very basic diagram of an eye. So let's now look at how the eye basically works, and what we'll have is we'll have someone a long distance away, the classic distance object, and you know that the light therefore runs parallel. We'll do the initial one first and then up the top, and we know that, remember that most refraction occurs at the cornea because this is air, where the air then hits the eye, so we have the most bending here. The light then further gets bent at the lens before we get a focusing of the image. So let's just look again, most refraction at the cornea, a bit of fine tuning by the lens, and then we get the upside down image of our person, and then this information then travels by the optic nerve to the brain, and so you can see a lovely focused person that you can see. Now, if you remember from Dr. Youssef's lecture, we have this formula with regards 1 on F equals 1 on DI plus 1 on DO, and that's the lens formula. And with respect to the eye, it's a bit different from what you did in the lab, where you could shift the position of the screen that was viewing the image, because of course the retina really is the screen that views the image that is produced by the cornea and lens of the eye. So therefore DI is here. And so it's not going to change, because you cannot change where your retina sits with regards to the rest of your eye. You don't change the shape of your whole eyeball. So therefore this value, DI, is fixed. So the distance of the object, therefore, is going to have the greatest effect on what your value of F is. Now, F, of course, is the focal length of the lens. Now, remember, Dr. Youssef said in the lecture that the lens finally adjusts. And the way that it finally adjusts is that the lens will change its shape. And when it changes its shape, it changes its value of F, which then allows you to focus objects on the retina. So, depending on how much DO changes by, will determine how much your value of F is going to change by. So for example, if the distance of the person that you're looking at here, who's far, far away, is 400 meters, if they move a little bit closer, let's say 5 meters, then the value of DO of 1 on DO isn't going to change much. You're going to go from 1 on 400 to 1 on 395. So therefore, this value doesn't change much, so therefore your value of F doesn't change much, and therefore you could probably still focus without having much change in your lens. Now let's go to our bottom eye. This is the same eye here. You can see the lens is the same. We have the cornea and the retina here, so that everything's the same. But now what we're going to do is we're going to move our person up nice and close. So now our person, and of course this obviously is not to scale, this person is now 5 meters away from your eye, so you're not too far away at all. And so what happens here is again, the light now when it travels, it's not going to be travelling parallel because it's a lot, the object is a lot closer, and so the cornea will refract. There we go, let's do those light rays. The cornea will refract some, the lens will refract some, but now what happens, there now, when we focus the image of the person here, you can see that because the person is so close and the angle of the rays hitting the lens is not the same as it was above in this diagram, now the lens can no longer focus the image on the retina. Instead, the image is being focused here behind the retina. And that means that what is on the retina, which is what gets, remember, sent to your brain, is not going to be a clear image. It's going to be fuzzy. And if you remember again from your lab, when you shifted the screen away from the focal length of the convex lens, what happened? The image became fuzzy. And that's exactly what your eye would see if you didn't what we call accommodate. And so what happens is that the lens will go through a process that we call accommodation. And in that process, what happens is the lens will change its shape. So let me just try this. I'll get rid of our lens, as you can see there. And now what I'll do is make the lens more bulgy. Now if we make the lens more bulgy, we change the perpendicular, so it's a lot more sharper. If you look here, the perpendicular is in this direction. When you look here, the perpendicular is here. So what will happen is, remember, the light will get bent towards the perpendicular, and let me just do this in blue. So again, we see the rays into the lens are going to be the same because, of course, the cornea doesn't change its shape. But now the lens has changed its shape, so now the light gets bent more by the lens, and now we get the focusing of the image on the retina. So if an object gets closer to you, what you do is you change the value of f in order to allow the focus or the image to be focused well on the retina. And this process is called accommodation. And yes, when you spell it, there is 2 C's and 2 M's in accommodation. So you are going to look at this more when you do your neuroscience. And also in Dr. Clare's lectures, you'll learn about the muscle called the ciliary muscle and the ligaments, which are called the suspensory ligaments, that help control the shape of the lens. Anyway, I hope this has helped you understand a bit more how the physics that you're learning is integrated with material that you're going to cover a little bit later. Thank you very much.